Hello everyone. Today we are going to discuss about the torque equation and performance characteristics of DC motor as part of our DC machines course. So in this lecture we are going to study the derivation for the torque equation of a DC motor, and also we are going to study the performance characteristics of DC motor. The performance characteristics of DC motor, basically they are drawn between the torque, speed and the armature current. So basically how these three terms are related and how the characteristics vary with varying one factor, how the other factor varies is going to be seen under the performance characteristics of DC motor. So moving on to the first slide. So we can see that when a DC machine is either loaded as motor or generator. So when it is operating as either as a motor or generator, we know that the rotor conductors carry current in it. So rotor conductors are nothing but the armature conductors. They carry the current in it when the Faraday's laws of electromagnetic induction principle is applied. So these conductors, we know that they lie in the presence of magnetic field. These magnetic field is set up by the magnetic poles which are present in the stator. So we know that there is a proper area being maintained between the stator and the rotor for the natural cooling process. So these conductors, they experience a force according to Lorentz law. So this force will exert a torque which makes the conductors move. So we know that the conductors lie on the surface of the rotor at a common radius from the center. So if we consider this as our rotor drum, if this is the center of, we know that the conductors are going to lie on the circumference of the rotor. So consider these as the conductors which are lying on the circumference of the rotor. So hence a torque will be produced around the circumference of the rotor. So then the rotor starts rotating. So this is how the rotor in the motor starts rotating according to Lorentz force law and the Fleming's left hand rule. We know that the direction of force which is exerted on the conductors is given by Fleming's left hand rule. So when the machine operates as generator at a constant speed, this torque will be equal and opposite to that exerted by the prime mover. So when the machine operates as motor, this torque is transferred to the shaft of the rotor and thus drives the mechanical load which is attached to the shaft of the rotor. So this is how the torque is required in both, either when the DC machine is acting either as generator or motor. So in generator, we have seen that when it is maintained at a constant speed, the torque is equal and opposite to that of the prime mover. And in motor, we are seeing that the torque is transferred to the shaft of the rotor such that it drives the mechanical load which is attached to the shaft of the motor. So the expression is same for both motor and generator. So now the equation which we are going to derive for the torque equation of motor and generator will be same for the motor and generator, as we have seen the EMF equation or the generated EMF equation is same for motor and generator. In the same way, we can consider the torque equation also same for the generator and motor. So when the current carrying conductor is placed in the presence of a magnetic field, a force is exerted, so which exerts a turning moment or a twisting moment called as torque. So this torque can also be called as driving torque. So as I told that the conductors are placed on the circumference of the motor drum, so we can consider that the torque is given as the product of force exerted on the conductors multiplied by the radius of the drum of the rotor. So this is how we write the basic expression for the torque. So as this torque is produced by the electromagnetic induction in the rotor conductors, as we know that the electromagnetic induction is nothing but when the rotating conductors, now the conductors are rotating in the presence of a stationary magnetic field. So in the presence of this stationary magnetic field, we know that an EMF will be induced in the conductors. So this is now nothing but called as electromagnetic effect, which we can see, which we are studying from the starting of our course. So very important. So based on this effect, this torque which is exerted, or this turning or twisting moment which is exerted on the generator or rotor, can also be called as electromagnetic torque. So we have to derive the equation for electromagnetic torque. Before that, we are going to see, so consider that torque which is produced in the armature is not fully used at the shaft for doing the useful work. So some of it gets lost due to the mechanical losses. So there is a loss of torque in the form of mechanical losses, The torque which is actually used for doing the useful work, that is converting the electrical input to the mechanical output, is nothing but called as shaft torque. So as we have seen that some of the torque gets lost in the mechanical losses. So some of the remaining torque which is useful for doing the actual work in the motor is nothing but the shaft torque. So we know that the voltage equation for motor is nothing but the back EMF which is equal and opposite to the applied voltage across the motor plus the drop in the armature conductors. So we can see that this is the back EMF and this is the drop across the armature conductors. So multiplying this equation by IA, we will get the power equation. So this is nothing but the electrical input which is given to the motor, and this is nothing but the mechanical power developed in the motor, and this is nothing but the losses due to the armature resistance or the armature windings in the rotor. So we can see that V into IA is the electrical power input to the armature. We know that the input to the motor is nothing but the electrical input. So based on that, V into IA, V is nothing but the supply voltage, IA is nothing but the current which is supplied to the armature. So together, the product of the supplied voltage and the armature current together is called as electrical input, and EB into IA. We know that the back EMF is generated in the rotor of the motor. So when it is multiplied by IA, so we will get the mechanical power which is developed across the motor, because the output of the motor is drawn from the rotor conductors. So that's why we know that the output of motor is nothing but the mechanical power. So the mechanical power is obviously developed across the rotor. So it is nothing but the back EMF multiplied by the armature current. So this back EMF multiplied by armature current is taken as PM. This is taken as electrical power, and this is taken as the losses, the copper losses. So total electrical power supplied to the armature is equals to the mechanical power developed across the armature plus the losses in the armature resistance. So from this we can write the equation for mechanical power as EB into IA. Also the mechanical power, if we take it in terms of torque, if we want to write the mechanical power which is developed or the mechanical power which is lost in the form of torque, the torque which is lost in the form of mechanical losses, if we want to write the mechanical power in terms of torque, we can write it as 2 pi n into T. So we can simply write it as, we know that 2 pi n is nothing but our omega, angular velocity with which the rotor drum rotates. So if we write it in the terms of angular velocity omega, we can write the mechanical power as PM is equals to 2 pi n into T. So when n is the revolution speed when n is the revolution per seconds and T is the torque in Newton meters, we know that the units for torque is nothing but the Newton meters. When we consider n as the revolutions per second, we can write 2 pi nt, that is this equation, the mechanical power. We can equate both the mechanical powers in equation 3 and equation 4. So we can write it as 2 pi n into T, which is equated to EB into IA. So from this we can rewrite the equation for torque as EB into IA by 2 pi n. So we know that the back EMF or the generated EMF has an equation phi z np by 60A. We know that the terms Z, N, P, 60 and all this we have derived in the equation of EMF equation of DC generator. The same EMF can be considered for the DC motor also. So substituting this EB value in the equation number, in the torque equation which we have got in the previous slide, we get and when we take N in RPM, that is in rotations per minute or revolutions per minute, when we consider the speed in revolutions per minute, we take the N as N by 60. As we are converting the seconds term to the minutes term, as we are converting the revolutions per second into revolutions per minute, so we are going to replace that N by 60. So where N is the speed in RPS, that is a small n, the lowercase n is the speed in RPS and the higher case or the uppercase n is the speed in RPM. So substituting that Further, we will get the torque equation as T is equals to phi ZP by 2 pi A into IA. So when we know that your ZP, the number of parallel paths, and your armature current and the flux is going to vary. So I can write this as 0.159 into phi ZP into IA by A, where phi is the flux in Webers, Z is the number of conductors in the armature, P is the number of poles in the stator, and A is the number of parallel paths, and IA is the armature current. So this is the torque equation which we consider for the DC motor. From this we can see that all these terms are constant. When these terms are constant, that is the number of conductors, number of poles, and the number of parallel paths, when they are made constant, so my torque is directly proportional to the product of flux which is developed in the main poles and the armature current which is developed in the armature. So for a particular DC motor with P number of poles and number of conductors in particular parallel paths, so I can take this K as constant as these values are constant. So from this torque equation, I can say that my torque in the DC motor is directly proportional to the product of flux and the armature current. So from this equation phi, it is clear that the torque produced is directly proportional to the flux per pole and the armature current. Moreover, the direction of electromagnetic torque developed in the armature depends on current in the armature conductors. If either of two is reversed, the direction of torque, if IA is reversed or is reversed, then the direction of torque is also reversed, hence which also reverses the direction of rotation of motor. So, but when both are reversed, the direction of torque does not change. If any one of the term, either phi or IA, are reversed, the direction of the torque reverses, and this reverses the direction of rotation. But when both together, the flux and the armature current, are reversed, so the torque does not change. The direction of torque does not change, and it will not change the direction of rotation of the motor. So this is the torque equation. So from the torque equation, it is very clear that the torque is directly proportional to the product of flux multiplied by the armature current. So moving on to the performance characteristics of DC motors, we basically have three performance characteristics. The characteristics curves which are drawn between the torque and armature current, T versus IA, and the characteristics which are drawn between the speed and the armature current, that is nothing but N versus IA, and the last one is torque versus speed or speed versus torque characteristics. So these are the basically three characteristics which we analyze for the three different types of motors which we have. So we know that we basically have series motors, shunt motor, and compound motor. For each type of motors, these characteristics are mainly explained with considering two relations. That is nothing but the one relation, the armature torque is directly proportional to the product of flux and the armature current, and the next relation which we get from the EMF equation or the back EMF equation of the motor. So we know that EB is directly is equals to phi ZNP by 60A. So from this relation, if I write my speed is directly proportional to EB by phi. So these two relations are required to have a knowledge or to understand about the performance characteristics of DC motors. So in DC motors, we know that the back EMF is given by phi ZNP by 60A. For a machine, P, Z and A are constants. That is why the speed is directly proportional to EB and inversely proportional to the flux per pole. So these are the basically two relations which we need to understand in each and every type of motor. So moving on to the first, the characteristics of DC series motors. So characteristics of DC series motors, which is also called as electrical characteristics, as we know that the torque is developed in the rotor and the armature current is also developed in the rotor. We know that from the torque equation, the torque is directly proportional to the flux multiplied by Ia. So in a DC series motor, we know that field winding is connected in series with the armature. So this is the field winding, this is the armature winding. So when they are connected in series, I can consider that my armature current and the field current both are same. As we know that in electrical circuits, the current is same in the series connected circuits and the voltage is same in the parallelly connected circuits. So as this is a series motor, my field winding and the armature winding are connected in series. So that's why I'm considering the single current, that is armature current is equals to the series field current. So therefore, before magnetic saturation of the core, the flux phi is directly proportional to Ia. That is nothing but with the increase in flux, the armature current increases. So we can, from the torque equation, we can say that the armature torque is now proportional to Ia square. So until the saturation, let us consider this is a saturation point of core. So till here, the curve represents the rectangular hyperbola. That is nothing but the armature torque is proportional to the square of armature current. That is T is proportional to Ia square. So after magnetic saturation of the poles, the flux is independent of armature current now. So that's why I can straight away say that my torque is now directly proportional to armature current. So as the armature current increases, the driving torque also increases. So after the magnetic saturation point, we can see that there is a straight line, that with the increase in armature current, we can find the increase of torque. So we know that armature torque is dependent on the flux phi and Ia, and shaft torque is less than the armature torque. So that's why we find the shaft torque. This shaft torque is less than the armature torque due to the stray losses. So these stray losses will reduce the value of shaft torque. So that's why the curve for shaft torque always lies below the armature torque line. So that's why this is a point of magnetic saturation. So till the magnetic saturation, we can see the curve as rectangular hyperbola. After the magnetic saturation, there is a linear graph between the armature torque and armature current. So this is about the electrical characteristics, that is nothing but the armature torque versus armature current characteristics of a DC series motor. So that's why prior to magnetic saturation, torque increases as the square of the armature current. So for a small value of Ia, there is a very high increase in the armature torque. So that's why these series motors require high starting torque, are used in the applications where they require high starting torque. So that is why DC series motor is never started unless and until it is loaded. So moving on to the next characteristics, speed versus armature current. So speed versus armature current. So we can see that we know the relation, the second relation, speed versus armature, from the EMF equation or the back EMF equation of the motor. We have the relation for the speed of the motor as is directly proportional to the back EMF and inversely proportional to the flux per pole. So for small load currents, that is for small armature currents, the change in back EMF is very small and it may be neglected, or it can be taken as almost constant. Hence for small currents, speed is inversely proportional to flux, and we know that flux is directly proportional to current Ia. As speed is inversely proportional to Ia, for a small increase in Ia, the speed value decreases. So when armature current is very small, the speed becomes dangerously high. So for small change in Ia also, the speed will become dangerously high. So that is why we should always consider that series DC motor should never be started without loading it with a mechanical load. So always remember, before starting the series motor, DC series motor, it should always be loaded. But at heavy loads, we know that IA is very large. And now in this particular case, when IA is very large, the speed decreases, as there is a directly proportional relation between the speed and EB. When speed decreases, the EB also decreases, which allows the more armature current into the rotor of the motor. So this is about this speed and armature current. So we can see that as the armature current increases, the speed slowly drops. So this is nothing but the rectangular hyperbola curve. The relation between the speed and armature current is nothing but the rectangular hyperbola. Next, moving on to speed versus torque. So the last characteristics of DC series motor. So from the above two characteristics, we have seen that till magnetic saturation, the torque versus IA is hyperbola, and then it is a linear graph. And for speed versus current, we have seen that it is a rectangular hyperbola. As the IA value increases, your speed slowly drops. So from the above two characteristics, we can see that when the speed is high, the torque is low. And when the torque is high, the speed is low. So when the torque increases, the speed slowly drops. So initially, when the torque is low, the speed is high. At this value, the speed is high. And when the torque is high, as we increase the value of torque, the speed slowly drops. So this is the speed versus torque characteristics of DC series motor. So these are the three characteristics, that is torque, speed, torque and armature current, speed and armature current, and speed and torque characteristics of a DC series motor. So from these characteristics, we can see that your DC series motor is applied where the loads require high starting torque, and also your DC series motor should never be started without loading it. Moving on to the next, the characteristics of DC shunt motors. So the same three characteristics will be now analyzed for shunt motor. So when it is a shunt motor, we can see the field winding connected in parallel with the armature. So in case of DC shunt motors, we always assume that the field flux to be constant. This is the field winding. The field flux will always be assumed to be constant in shunt motors. So though at heavy loads, your phi decreases in small amounts due to the increased armature reaction. So we have seen that armature reaction is nothing but the effect of armature flux on the main field flux. So when there are heavy loads applied on the DC shunt motors, the flux decreases in small amounts. So basically, we consider it as a constant flux machine. The DC shunt machine is considered as a constant flux machine. So when there is loaded heavily, there is a slight decrease in the flux due to armature reaction. So as we are now neglecting the change in the flux, as we are considering it the constant motor, constant flux machine, so we can say that the torque is directly proportional to armature current from the torque relation. So as there is a directly proportionality relation, when we increase the armature current values, the torque will increase. So there is a linear graph between the torque versus IA characteristics. So we know that the shaft torque is always less than the armature torque due to the stray losses. So that's why it is also a linear graph. The shaft torque is also a linear graph between the armature current and the armature torque. So hence, for a DC motor, it will be the straight line passing through origin. So heavy starting load needs heavy starting current. So shunt motor should never be started on heavy loads. So this is the quite opposite case to the DC series motor. DC series motor should always be started with loading, and your shunt motor should never be started by loading it heavily. Moving on to the next characteristic, speed versus armature current. So we can see that from the relation, speed is directly proportional to EB. As we are saying that it is a constant flux machine, so your back EMF is also almost constant. The speed also should remain constant in this particular case, as speed is directly and EB is directly proportional to phi ZNP by 60A. So from this, practically, so phi as well as EB decreases with increase in load. So when we increase the load, the armature current drawn by the rotor will increase. Hence, the EB will also decrease. So that's why the flux phi and EB will decrease when we increase the load on DC shunt motor. So back EMF decreases slightly more than the flux. Therefore, the speed decreases slightly. Generally, the speed decreases only 5 to 15% of the full load speed. This is the range of speed which we decrease in the range of speed compared to the full load speed, which we can expect when there is a decrease in EB and phi when the motor is loaded. So from this we can see that at no load, the graph between the speed and the armature current, as we know that at no load it is a constant flux machine. So as it is a constant flux machine, EB is also almost constant, and hence your speed is also constant. So that's why we can see a straight line. So this fall in characteristics is due to the armature reaction or the drops across the armature coming into picture. So that's why there will be slightly drop in speed when the armature current increases when the motor is loaded. So therefore, your shunt motor can be assumed as a constant speed motor. If the speed versus armature characteristics in the following figure, the straight line represents the ideal characteristics and the actual characteristics is represented by this dotted line. So from this we can come to a conclusion that your shunt motor can be considered as the constant speed machine. Coming to the torque speed characteristics, as the torque increases, the speed of the motor should decrease. So which we can see in this graph. So as the torque increases, we know that torque is proportional to phi into Ia and EB is proportional to N. So N is proportional to EB by phi. So this is directly related to phi and this is inversely related to phi. So when we take the previous two characteristics into consideration, so when flux is maintained constant for this kind of shunt machines, your torque remains constant. But if there is sudden decrease or increase, there is sudden decrease in the flux, there will be decrease in the armature torque, but vice versa, there will be the increase in speed. And when we increase the torque, this case becomes exactly opposite. So when we increase the armature torque, your speed slowly falls down. So this is nothing but the speed and torque characteristics of DC shunt motor. So moving on to the DC compound motor. So we know that compound motor, we have two types. One is differentially compound motor and the one is cumulative compound motor. So in compound motor, we know that we have two field windings. One is series field winding and the other is a shunt field winding. This is a series field winding and this is a shunt field winding and this is the armature winding. So we know that when the flux in the series field aids with the flux in the shunt field, then it is called as cumulative compound motor. And when the flux in the series field winding opposes the flux in the shunt field winding, then it is called as differential compound motor. So we are going to see the circuit of the compound motor. We now have our series field also here, which is connected to the external load. This is the series field winding, this is the armature winding, and this is the shunt field winding. So when the flux in the series field winding aids the flux in the shunt field winding, and that kind of motor is called as cumulative compound motor. When the flux in both the field windings oppose with each other, then that is called as differentially compound motor. So when we see the characteristics of torque versus armature current, we can see this for the series motor, it is like this, and for the shunt motor, it is a linear graph. So for cumulative, we can see that as the flux is aiding with each other, so we can see that the curve for cumulative compound motor is lying above the shunt compound motor. So for cumulative compound motor, the flux is high, so we know that the torque is directly proportional, right? So when two fluxes are aiding with each other, we know that the resultant flux is high, so that's why the torque is also high. So we can see that for a cumulative compound motor, the torque versus armature current characteristics are similar to the series field, but it is always lying below the series DC series motor curve. And for the differential compound motor, we can see that the flux will oppose with each other, so the resultant flux will decrease, which decreases the torque value, armature current value. So when the armature current increases also, the torque is almost a linear graph, so it is always lies below the DC shunt motor characteristics. So for cumulative, it is above the shunt motor, DC shunt motor characteristics, and for the differential, it is below the DC shunt motor characteristics. So moving on to the next characteristics here, it is nothing but the speed versus armature current. So we have the relation for speed as EB by phi. So we know that cumulative compound machine is nothing but in which the flux, the resultant flux is high. So that's why we can see the dropping characteristics of the speed here. And for differential compound, the flux is low, the resultant flux is low. So that's why we can see the characteristics between the speed and armature current are increasing. For the increasing values of Ia, the speed is also increasing. Moving on to the last characteristics, that is nothing but the speed versus torque. So from the two relations again, EB by phi. So from these two relations, we can see that as torque increases, as the flux, resultant flux for a cumulative compound machine is high. So that's why the torque increases for cumulative compound machines. For differential compound machines, we can see that the curve for cumulative compound machines is nothing but when the torque increases, the speed decreases. And exactly the opposite to this, when the torque increases, as a resultant flux is low here, as a resultant flux in the differentially component machine is low, the speed increases. So this can be seen in this particular curve. So these are nothing but the characteristics of all the three kinds of motors. So in today's class, we have discussed about the torque equation and the derivation of the torque equation. Then we have discussed about the performance characteristics of all the three kinds of motors, that is series, shunt, and compound. We know that the performance characteristics basically are nothing but torque versus armature current, speed versus armature current, and the last characteristic is nothing but speed versus torque. We have analyzed all these three characteristics with different curves for all the three kinds of motors in today's lecture. Thank you.